Okay, in this video, our goal is to connect time-varying integrals of quantities, right? So that's what I've learned over here, time-varying integrals of quantities. And what I mean by that is a global quantity such as the total mass or the total energy, E, or in general, the total stuff, B, right? In a control mass and relate that to a control volume. And I want to emphasize again right at the outset that this is really not a basic principle. It's really a bookkeeping principle, if you will. Right. So that's what we're after in this video. And just a comment, if you look at all the basic principles that were laid out in another video, all of them have this format. The rate of change, ddt, of some quantity B, and the quantity B would be mass. If it were a conservation of mass statement, the quantity B would be m, the momentum, with it's got a vector, so it's got the vector symbol on top. If it were Newton's second law, B would be the total energy, E, or B would be entropy, total entropy inside my control mass if I'm talking about the second law of thermodynamics, which is something that we are really not discussing in this course. But nevertheless, all of them have a similar framework. That's the point I want to make here. All right. So that's for conservation of mass, that's for Newton's second law, that's for energy, that's for second law of thermodynamics, right? And what does this B look like? The B always looks like this integral. So it's an integral over a volume, and the volume is rho dV, remember, gives the mass, and then multiplied by this quantity B. And what does that quantity B look like, right? If I take B equals 1, clearly I'm going to integrate this quantity with B equals 1 is going to give me, the total result is going to give me M, the mass, right? Because all I'm doing is rho dV, and then I'm adding all these pieces. If on the other hand, B has the value V, then I'm talking about Newton's second law. B, remember, is the velocity of the fluid measured with respect to an inertial reference frame. So everywhere I have rho dV is the mass, and then I multiply that by the momentum in that region and add all of them together. Essentially, then I'm going to get the total momentum, M. Okay. Same way, if B were to be the energy per unit mass, and then I multiply the mass by energy per unit mass, gives me the energy. I add all this piece of energy or integrate over the volume, I'm going to get the total energy, E, so on, right? And B would be a little less if I'm talking about the entropy, entropy per unit mass, all right? Now let's look at this integral, rate of change of this integral rho B dV over the volume occupied by the control mass. All right. And if you go back from a fundamental definition in calculus, I can write this derivative as simply the limit as delta t approaches 0. Delta t is a small time step, if you will, where I take this integral rho B dV over the control mass, and the control mass may occupy a different location in space at a new time, t plus delta t, and subtract it from its original value and divide that difference by delta t. That's what gives me the first derivative, right? So in other words, if I have a function f of x, I'm going to take f of x plus delta x minus f of x, and I'm going to divide by delta x, and then take the limit of this as delta x approaches 0, right? That's what is going to give me the derivative f prime of x. Same concept we are using over here. All right, so this control mass volume, that's what the CMV indicates. So the control mass volume is going to be the volume of this region in space where the control mass is occupied. And I'm going to make the assumption that for this argument over here, that the control mass and the control volume are coincident at time t. Okay. The next integral, which is this one right here, is going to be the control mass, let's say, moves to a different location and also changes its shape. Then I need to account for this integral over this new blue region shown by this new blue line labeled Cm at t plus delta t. All right. So that's really what's happening inside this definition, if you will, of the derivative ddt of rho b dv on the left-hand side over a control mass integral, right? Now let's imagine that at this new time, the control volume and the control mass, which are originally coincident, but the control volume could have a different region in space right here. And so I'm labeling that as control volume at t plus delta t. So our goal in this situation is to connect the time-varying integrals of quantities such as mass, momentum, energy, etc. inside a control mass and relate that to the time derivative with respect to a control volume. All right, so I'm going to copy the expression from the previous slide for the time first derivative of integral of rho b dv over the volume occupied by the control mass. That's what I call CMV. And this is the same thing, the definition of the first derivative. It's the volume at t plus delta t minus the integral over the volume at time t divided by delta t. All right. Now, in this equation, I label this as equation 1. In this equation, if I look at this term right here, integral of rho b dv over the control mass volume, remember the control mass volume and the control volume were coincident at time t. So in other words, this integral, which is this one sitting up here, I can replace that as the integral of rho b dv, except now I'm performing the integration over the control volume as opposed to the control mass volume, right? Because the two are coincident at time t. If I take the second integral, or the integral that appears, which is, I guess, technically the first integral that appears in equation 1, and think about that for a minute, right? So this is going to be the integral over this control mass at time t plus delta t, right? Now, however, I want to bring in the control volume and relate it to the integral over the control volume. So this would be equal to the integral over the control volume at t plus delta t, provided I take into account sort of the difference in between the control mass and the control volume, which is shown by these shaded regions, right? So if I take this piece and this piece over here, so in other words, if I would add this piece and then I subtract out this piece, then I'm basically from the red region, then I'm basically going to get the blue region, right? And I'm going to label that piece, the plus and the minus all put together, as this region 2, if you will, right? And so it is the integral over the control volume plus the integral over this region, which I call pi, occupied at time t plus delta t of the same quantity rho b dv, right? And let's focus on this volume over here over this region pi, okay? And in order to do that, I'm going to zoom in at a region at the edge of the control volume and look at it and blow it up, okay? So the blue line represents the control mass edge. The red line represents the control volume edge, right? And let's imagine that the control volume is moving at a speed vrel relative to the control mass, okay? And let's imagine that the area vector associated with this is dA, okay? And if I take this quantity dV, is basically this region right here that we are talking about, the region 2, which is this region right here. That volume is the volume dV that I'm interested in. So it's simply vrel dotted with dA times delta t, right? So if I take the relative velocity multiplied by delta t, that's going to give me the distance over here, this distance, okay? And if I multiply that by the area of cross section, that's going to essentially give me the volume in this segment, or in this portion, okay? And the fact that in some region we got to subtract, in some region we got to add to make the two figures coincident, is all taken into account with this vrel.dA term. So wherever it is less than 0, then you have inflow of matter into the control volume, and where vrel.dA is greater than 0, then you have outflow of matter from the control volume, right? So the way I've shown over here is the relative velocity vector is pointing in this direction, the area vector is pointing in this direction. I got an obtuse angle, in which case the dot product is going to be negative, correct? And so if it is negative, then I have inflow of matter into my control volume. So let's rearrange what we got from the previous slide as equation 2. So this is now, if you go back and think about this, this is simply the same as this, except the integrals are being performed over the control volume, okay? So I can replace this as the time rate of change of the same quantity, b, but now it's performing the integration over the control volume. And the difference is this extra term, which is the integral over the region pi, which I'm now replacing this dv in terms of vrel dot over dA times delta t, all right? And clearly, if I think about this term right here, the delta t's are going to cancel out, okay? And so what I'm left with is the rate of change of the B stuff inside my control mass is the rate of change of my B stuff inside my control volume, plus this is essentially the net outflow minus inflow of B stuff going out, in and out of my control volume. So that's what equation 3 represents. And this is what's called the Reynolds transport theorem, right? So the Reynolds transport theorem really connects the rate of change of B stuff within my control mass equals the rate of change of B stuff within my control volume, plus the net outflow minus inflow is the net outflow, you can call it, rate of the B stuff. B could be mass, B could be momentum, energy, etc., that goes across the boundary of the control volume. So in other words, the Reynolds transport theorem is simply a bridge that connects control mass integrals, time integrals, to control volume time integrals. And I want to emphasize one more time, this is not a physical law or a principle, it's simply a bookkeeping or a balance statement. One final comment I'll make over here is, now that I have Reynolds transport theorem, which provides the bridge, now I can start extending my basic principles, which we initially wrote them down for a control mass, and start thinking about writing those basic principles for a control volume. And that's where the Reynolds transport theorem, the bridge, if you will come in handy.